Simplex method visualized. In this video, I'll show you how the simplex method actually works visually and step by step. We'll solve a product mix problem graphically, then using the simplex method, and finally interpret the shadow prices. Let's consider a company that produces two products. Let X be the number of units of product 1, and X be the number of units of product 2. Each unit of product 1 generates a profit of 3, and each unit of product 2 generates a profit of 4. Our goal is to maximize total profit. So the objective function is maximize z equals 3x plus for x. Now we add the constraints. The first constraint is x plus x less than or equal to 4. The second constraint is to x plus x less than or equal to 6. The third constraint is x plus 3x less than or equal to 9. And both variables must be greater than or equal to 0. First, let's solve this problem graphically. We draw each constraint as a line and identify the feasible region that satisfies all constraints. Next, we identify the corner points of the feasible region. These are the candidate solutions. We evaluate the objective function at each corner point. The point that gives the highest value is the optimal solution. In this case, the optimal solution occurs at x equals 1.5 and x equals to 0.5. This gives a maximum profit of 14.5. Slack variables and Tableau setup. We now move from the graphical method to the simplex method. First, we convert each inequality into an equation by adding a slack variable. So constraint 1 gets S1, constraint 2 gets S2, and constraint 3 gets S3. These slack variables measure unused resources. We then write the objective row as z minus 3 times 1 minus 4 times 2 equals 0. This is the initial simplex Tableau. The starting basic variables are S1, S2, and S3, so the initial corner point is x1 equals 0 and x2 equals 0. To choose the entering variable, we look at the z row and pick the most negative coefficient. Since -4 is the most negative, x2 enters. Using the ratio test, S3 leaves, so the pivot element is 3. Now we perform the first pivot. First, divide row 3 by 3 so the pivot becomes 1. Then clear the other entries in the x2 column. We do row 1 minus row 3, row 2 minus row 3, and 0 plus 4 times row 3. This creates a new tableau where x2 becomes a basic variable. After the first pivot, x2 is basic with value 3, and x1 is still 0. So the new corner point is 0, 3. Now we check the z row again. Since -5/3 is still negative, x1 enters next. Using the ratio test on the x1 column, S1 leaves. So the next pivot element is to over 3. For the second pivot, we make the pivot entry to over 3 into 1 by multiplying row 1 by 3 over 2. Then we clear the rest of the x1 column. We do row 2 minus 5/3 times row 1, row 3 minus 1/3 times row 1, and 0 plus 5/3 times row 1. This gives the optimal tableau. Now we read the optimal solution from the final tableau. The basic variables are x1 and x2. So x1 equals 3/2 and x2 equals 5/2. The objective value is 29/2, which is 14.5. The simplex path moved from 0 to 3 to 3/2, 5/2. This matches the graphical solution exactly. Now let us look at what is happening. We begin at the origin, where both decision variables are 0. This is our initial basic feasible solution. The simplex method identifies a direction that improves the objective function. After the first pivot, the solution moves to the point 0, 3. From there, the method continues improving the solution. After the second pivot, it moves to the point 1.5, 2.5. Each pivot in the simplex method corresponds to moving from one corner point of the feasible region to another. Now let's write the dual problem. Since the primal is a maximization problem with less than or equal constraints, the dual will be a minimization problem with greater than or equal constraints. Each primal constraint creates one dual variable, so we introduce y1, y2, and y3, one for each resource constraint. We solve the dual using complementary slackness. From the primal optimum, x1 and x2 are both positive, so both dual constraints must hold as equalities. Also, the second primal constraint is positive slack, so y2 must be 0. That gives us two equations in y1 and y3, which we can solve directly. Solving those equations gives y1 equals 5/2, y2 equals 0, and y3 equals 1/2. These are the shadow prices. The dual objective value is 29/2, or 14.5, which exactly matches the primal optimum. This confirms strong duality. Now we interpret the numbers. A shadow price tells us how much profit increases if we get one more unit of a resource. So one extra unit of resource 1 increases profit by 2.5. Resource 2 adds nothing at the margin, so its shadow price is 0. One extra unit of resource 3 increases profit by 0.5. We can read shadow prices directly from the final tableau. For a maximization problem with less than constraints, the coefficients in the z row under the slack variables give the shadow prices. Here, under S1, S2, and S3, we get 5 over 2, 0, and 1 over 2. These match exactly with the dual solution. Each shadow price tells us how much the objective increases if we add 1 unit of a resource. Resource 1 increases profit by 2.5. Resource 2 has no effect, and resource 3 increases profit by 0.5. Only binding constraints have positive shadow prices, which explains why the second constraint is 0. Now we study how changes in the right-hand side affect the solution. If we change a constraint from b to b plus delta, the new basic solution becomes xb plus delta times a column of b inverse. The key idea is to keep the same basis and ensure all basic variables remain non-negative. For constraint 1, we use the first column of b inverse. We update the basic variables and require all of them to stay non-negative. Solving the inequalities gives -1 less than or equal to delta less than or equal to 0.2. So the allowable decrease is 1, and the allowable increase is 0.2. For constraint 2, only one basic variable changes. The condition gives delta greater than or equal to -0.5 with no upper limit. So the allowable decrease is 0.5 and the allowable increase is infinite. This matches the fact that this constraint is non-binding and has 0 shadow price. For constraint 3, we again use the corresponding column of b inverse. Solving the inequalities gives -1 less than or equal to delta less than or equal to 3. So the allowable decrease is 1, and the allowable increase is 3. We solved the same problem in 4 different ways. The graphical method showed the feasible region. The simplex method moved from corner to corner. The dual problem revealed the value of resources. Sensitivity analysis showed how changes affect the solution. All approaches lead to the same answer, giving both intuition and mathematical insight. LT text. If you need help with linear programming, optimization, or any math topic, visit w.mytutornyc.com. You can also call or text me at 6465430832, or reach me on WhatsApp at 0638413336. I offer personalized tutoring with clear, step-by-step explanations.